So if you've been working, you've seen in Appendix C, there's three columns. There's a delta H, a delta G, and a delta and an S. And so you just use the number from the second column here. I worked out an example. Let's say we have the balanced equation. We want to calculate delta G for the reaction. So we take the products first and we're going to add them together. So these are your delta GF numbers here in kilojoules. And I got a 2 there. That's your, if you have a coefficient, put that in front and then add those up, and then we're going to subtract from the reactant side. And you'll notice that delta G and delta H for free elements is 0. And that's important to know because sometimes when you get a test question, they're giving you these numbers, but they're not going to give you this one because you're supposed to know it's 0. And if you don't remember that, you're going to feel like you're missing something, missing a piece of information. So really, we could do this. We've got these three equations here. We can calculate delta H, enthalpy change, free energy change, entropy change for a given reaction using the appendix information in there. This is just an example of all three of those worked out. It looks like a lot of work, but it's pretty simple to do it. So I see for free elements like this, these two are 0, but entropy is not going to be 0. You got to have entropy if you're over 273 Kelvin. Let's see. And then I just mentioned here, sometimes you run into a problem where they're going to ask you for one of these thermodynamic quantities, and they'll give you the number for the overall reaction. Most of the time you're finding this number, but you might see a question where you're given this number and they ask you for one of these over here. But if you know what the equation is, and then you just put the numbers in the correct place, solve for the one you don't know. Pretty straightforward. Okay. Now, getting on to what temperature will a process change if it's temperature dependent between spontaneous and non-spontaneous. And you'll be doing this in these part of your homework, 66, 69, 70. So what we want to do is, the number is going to, somewhere it's going to be, these two are going to be equal to each other if they have opposite signs. So either this is negative and this quantity is positive, or this is positive and this is negative. So either both these are positive, this is positive, delta is positive, but they're both negative. That means that at some temperature, those two are going to add together to be 0. That's your temperature dependent process, what you're going to have. And so if we put in 0, our equilibrium condition, and then we'll just solve this equation for T, we come up with this. Now, of course, this is not going to be on your sheet. This one will be. You just need to remember when you want to find the temperature for a temperature dependent process, you just put in 0 for delta G and isolate T. For example, just to kind of see how this works, if we take the process of water boiling, so this would occur, equilibrium would be at the boiling point, which we know is 100 degrees Celsius or 373 Kelvin. And so we could do find the delta H for that. This would be endothermic because you're boiling, adding energy. This is your delta S, and then divide that, and you get 370 Kelvin, which is pretty close to the boiling point. Remember, delta H and delta S do change with temperature, so the measurements in the back of your book are for 298, so if you were at 373, your delta H and delta S would change a little bit. So we're just going to get kind of a ballpark number here. So what that means is this quantity is positive, this quantity is negative. It's endothermic and increasing entropy when you boil. So you'd have a positive and a negative. So at low temperatures, delta G would be positive, and then this number would be going up. And so when you got to 0 at 373 Kelvin, and then if you keep going up, then this negative sign will, or this negative term will become larger than delta H, and delta G will be negative from that point on. So you have some questions. At what temperature will this become spontaneous or non-spontaneous? For example, 66A says, this is one of your homework problems, and from the values given, calculate delta G, and if the reaction is not spontaneous under standard conditions, at what temperature, if any, would the reaction become spontaneous? So on the first part, we got a reaction, 2 lead sulfides plus 3 oxygens make 2 lead oxides and 2 sulfur dioxides. Gives us the delta H is negative, and it gives us the entropy is negative. So these are both negative. What's it mean when they're both the same sign? What's that tell you about the process? Temperature dependent, and when it's temperature dependent, the first delta H, this is the sign at low temperatures, so spontaneous at low, but becoming non-spontaneous at high. So we're going to find delta G first. That's pretty simple. Put in my given delta H value minus, I got the temperature, and then I put this number in now. Remember, this is going to be given in joules, and you need to change it to kilojoules. So you do want to divide that by 1,000 to change the number over. So I'm given negative 165 joule per Kelvin. I want it in kilojoules because this first number is in kilojoules. So I do that. These two together are about positive 49. And so when you add these two together, it's negative, so it is spontaneous at this temperature. As we increase T, this positive quantity is going to get bigger and bigger, and eventually it's going to equal positive 844, at which point we'll be at equilibrium. So at what temperature will delta G equal 0 is what we're really looking for here. So I just put in 0 for delta G, solve for T, that's just delta H over delta S. And I get the number 5,115 Kelvin. That's where it's at equilibrium. So if we go above that temperature, then delta G sign will change to positive, and this will become an unfavorable process. That's how you do that. A couple other side notes here. This I wanted to tie into some stuff we talked about earlier in the year, thermodynamics. So one thing we talked about was adding a solute to a liquid will lower its freezing point and raise its boiling point. And we can talk about that in terms of thermodynamics. So for example, there's a bunch of salt on the roads right now, and why did they go out and put salt all over the roads?
So it doesn't freeze.
Sidewalks. Yeah, they're trying to prevent freezing and ice on the roads and sidewalks. So why does that work? Well, one of the things we talked about last week was if you add a solute, a solution has more entropy than a pure liquid. And if the entropy increases, then the temperature at which equilibrium occurs, the freezing point, will go down. And the more entropy here, the lower that freezing point will be. So we put salt on the road, that increases the entropy of the water on the pavement, and that causes the freezing point temperature to go down. And if we look at that from the other way, the boiling point goes up. Now this is a little more complicated. So we have the same thing we talked about here. We've increased the entropy by adding a solute to the water. But notice here I've got decreased entropy, so why did I change that from increase to decrease? Well, we talked about when you add a solute like salt to water, you're increasing the intermolecular forces. You're changing it from hydrogen bonding to ion dipole, stronger force. That means it'll take more energy for liquid molecules to escape into the gas phase. So you're going to have less gas, lower vapor pressure. Remember when we learned all that, you know, what increases with, how did we go through all that? Adding, which properties of liquids increase when you add a solvent. And we talked about boiling point, melting point, and now what was I thinking about? What things are dependent on the strength of intermolecular forces? Everything was directly proportional, right? Boiling point, melting point went up